In 2022, a team at Google used a quantum computer to simulate a wormhole, and something passed through it. Headlines called it a real wormhole. Physicists called it something more complicated and more interesting. Here is what actually happened, why it matters, and what it does not mean. A wormhole, formerly called an Einstein Rosen bridge, is a theoretical solution to Einstein's field equations first described by Albert Einstein and Nathan Rosen in 1935. It connects two separate points in spacetime through a shortcut, a tunnel through the geometry of space itself. The mathematics permits their existence. The physics of whether they can actually exist in nature, remain stable, and be traversable by matter or information is a completely separate and unresolved question. The 1935 Einstein-Rosen bridge is not traversable. It collapses too quickly for anything to pass through. For a wormhole to stay open long enough to be useful, it would require exotic matter, material with negative energy density, to hold the throat open against gravitational collapse. Negative energy density exists in a limited quantum sense, seen in effects like the Casimir effect, but producing it at the scale needed to stabilize a wormhole is far beyond any known or near-future technology. So what did the Google experiment actually do? In November 2022, a collaboration involving researchers at Google, Caltech, MIT, Harvard, and other institutions published a paper in Nature describing an experiment on Google's Sycamore quantum processor. They created a simplified quantum system that behaves holographically like a wormhole, specifically using a concept called the ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind in 2013. ER equals EPR proposes a deep connection between two seemingly unrelated phenomena. ER stands for Einstein-Rosen bridge, a wormhole. EPR stands for Einstein-Podolsky-Rosen, the quantum entanglement paradox. The conjecture suggests that quantum entanglement between two particles is geometrically equivalent to connecting them with a wormhole. They are two descriptions of the same underlying physical reality. What the Google experiment did was create two small quantum systems, each containing a handful of qubits, entangle them, and then use a quantum teleportation protocol to send information from one system to the other. The information appeared to travel through the entangled quantum system in a way that, holographically, is described by the geometry of a wormhole in a lower-dimensional theoretical model called the Sachdev-Ye-Kitaev model. The researchers verified that the process had the properties expected of wormhole traversal in that model. Here is the critical distinction. This is not a wormhole through physical space. No shortcut was created through the fabric of the universe. No matter traveled faster than light. The wormhole existed as a mathematical description in a quantum simulation running on 9 functional qubits of a quantum processor. The system was so small and simplified that it offers no evidence that traversable wormholes can be built at macroscopic scales or that they exist anywhere in nature. Several physicists, including Sabine Hossenfelder, were direct about this. The experiment is interesting quantum physics and a meaningful test of the ER equals EPR conjecture. But calling it a wormhole in the physical sense is misleading. The distinction between simulating the mathematics of a wormhole and creating an actual wormhole is enormous. What the experiment does represent is real scientific progress on a deep question. The ER equals EPR conjecture, if correct, suggests that spacetime geometry and quantum entanglement are fundamentally connected. That would have profound implications for quantum gravity, the unfinished project of reconciling general relativity with quantum mechanics. Understanding that connection could eventually lead to a complete theory of quantum gravity, which is one of the most important open problems in all of physics. The Google experiment tested one specific prediction of the ER equals EPR framework at a small scale and found results consistent with it. That is meaningful. But it sits far upstream from any practical wormhole technology and cannot tell us whether wormholes exist in nature. The real wormhole question remains open. The mathematics permits them. The physics does not yet confirm them. And the technology required to test them at any meaningful scale does not exist. Follow for more on the frontier questions where quantum physics and general relativity collide. And tell me, Do you think the connection between entanglement and wormholes is the key to finally unifying quantum mechanics and gravity?